So welcome to a special lecture of Statistics 568, Design and Analysis of Experiments. We have a special bonus lecture for you today. It's going to be on the sugarcane data. We looked at it at the end of the last lecture in R, but it is a very good example of a fractional, three-level factorial design, and it's one that we can, assuming I don't slip on the ice here, it's one that we can use to better understand how these fractional designs work, because they are a little bit tricky and you can get some very strange things going on with the aliasing and the partial aliasing. So as an example, let's go take a half hour and look at that today. Welcome back to another lecture of Statistics 568, Design and Analysis of Experiments. Today we're going to end our discussion of 3 to the k factorial designs and then move into the idea of response surfaces in a separate part of today's lecture. But before we end our discussion on 3 to the k factorial designs, what I really want to do is go back and look at that sugarcane data that we examined in R at the end of the last lecture, because there's a lot that can be done here to help better cement the ideas of 3 to the k factorial designs, and specifically the fractional factorial designs in your mind going forward. So what I'd like to do is spend a little bit of time going through this in more detail on paper, that is on OneNote, and then after that we will conclude our section of 3-level factorial designs. So let's get into the notes. All right, so what we're going to do is we're going to discuss that sugarcane data. Sugarcane data set that we looked at last time, and this can be found, in case you forget, in the Chinloy, if I'm saying that correct, we'll just assume I am, fractional factorial data set, and this can be found in the Agridat package in R, which has just an endless supply of agricultural data sets, very many of which follow paradigms that we discussed in this course. But of course, there's actually some other interesting little quirks that they have in that data set, those data sets as well. So it's always fun to look at and see how they're actually analyzed, or how you actually analyze real world experimental design data. Right, so we already looked at this last time, but just to emphasize, this is a 3 to the 5 minus 1 design with factors N, P, K, B, and F. So those are our factors, and what we saw last time was that when we looked at the actual data, we found that, yes, it was a 3 to the 5 minus 1 design, so there were, 81 observations, right? 3 to the 4, just to emphasize how many data points we have to work with. And what that means is that there is one aliasing relation here in our data. And we didn't discuss exactly what that was in the last lecture. We just noticed that when we tried to fit a model and then look at the ANOVA table, we didn't have all of the possible interaction terms available. And in fact, even some of the two-way terms were missing some of their degrees of freedom. Remember, a two-way interaction, a complete two-way interaction without breaking it into its orthogonal components, should have 4 degrees of freedom. And then we can break it into 2 orthogonal components, each with 2 degrees of freedom. What we found there was that some of those were missing. The defining contrast subgroup, if you stare at the data long enough, or if you download the paper where it came from, which is quite old. I don't have R in front of me, so I forget how old it is, but yeah, the paper's dated a little bit. Regardless, what you would find is that they have aliased the interaction term p k squared b squared f with the identity. And just to emphasize, right, this is equivalent to saying that p plus 2k plus 2b plus f is equal to 0 mod 3. So if we imagine, I'm not going to write out all the columns, but we imagine what's going on here, right? We would have columns p, k, b, f, and then there's also, I guess, one of them is not included here, which is n. I guess n is also not included. But, right, we would have columns where we would say, okay, this is 0, 0, 0, maybe, 0, 0, 0, 1, 2, whatever. I guess I'm supposed to try to make them orthogonal, which is why I don't want them all to be 0, 0. Right, you get the idea, and then what we're effectively doing is we're summing them all up with this formula, and we're only including the rows where if we sum up these numbers, if we sum up p plus 2k plus 2b plus f, we should have 0 mod 3. So it's certain factor settings exist in our design. That is, there are treatments that are rows in our design matrix, and other treatments do not exist because we're not testing them because we're doing a fractional design. Anyway, right, so this is the defining contrast subgroup. There's only one element that we have to worry about, but it's still going to lead to some interesting complications. So, for example, if we want to figure out what n is aliased with, what we do is we would multiply n by, well, this element, which is n times p times k squared times b squared times f. But we also have to consider multiplying n squared by this same thing. Equivalently, we could square the big relation, this big defining, this p, k squared, b squared, f, if we really wanted to, and we'd get the same thing. So I can show you that just to make sure that's clear. But yeah, if we multiply n squared by the element of in our defining contrast subgroup, then what we should do is reduce it. That is, to get rid of the square in front of the n. Remember, this is for uniqueness, because if we don't do that, then we can run into some issues where we double count factors or interaction effects, and we don't want to do that. Alternatively, right, this is, if we put the parentheses around it, alternatively, I could write this as n p k squared b squared f all squared, which is also going to equal the same thing. So it is good to know that whether I square n or I square the four-way interaction term, when I reduce it, I'm going to get down to the same term. So these are the three things that are aliased together. So this is looking pretty good for n, right? N is strongly clear in the sense that it is only aliased in this case with five-way interactions. So it's actually even, I guess, better, because strongly clear just requires n to be aliased with four-way or higher interactions. In this case, we don't even have a four-way, we have a five-way. On the other hand, just to show in contrast, if we were to figure out what factor k is aliased with, we would have to multiply k by this thing, which is p k squared b squared f. When you multiply k by k squared, you get k cubed. Reducing mod 3 means that vanishes, and we're left with just a p b squared f. And if we were to multiply this by k squared, p k squared b squared f, then what happens is we end up with, we end up with a k to the fourth, which gets reduced mod 3 to just a k. Then we have a p k b squared f. So again, that looks a lot like the thing in the defining contrast subgroup, but there's no k squared there. So what we have here is, now let's do that one in blue. We have the two things, the two interaction effects that are aliased with k. So in this case, k is just clear, not strongly, because it's aliased with a three-way interaction effect. And we can do this again for F and P and B. The answers are in my notes online, my typed up lecture notes. So if you want to try it yourself, just to see if you understand how to derive the two other things that each of these main effects should be aliased with, you can do that. And you can also do that for the two-way interactions. I did that also on my online notes. It's not worth writing it all out in excruciating detail, but if you do have, I would try it yourself. And if you have any questions, just let me know, and I can work through these examples by hand. Now, one of the interesting things, though, I do want to note about the two-way interactions is what we find things like if we have a PF. Well, PF here, what's that going to be aliased with? That is going to be aliased with whatever PF times P K squared B squared F is, which in this case is going to be a P squared and F. I think I'm getting that out of order, but that's okay. Let's do K squared B squared F squared, which reduces, if we reduce everything by squaring it so that the first term has a coefficient or an exponent of 1, we turn all the 2's into 1's and get something like that. But if we multiply this by PF squared, now things become a little bit more interesting. What we end up with here is, well, we end up with a P cubed and an F cubed, which both vanish because they're taken to the third power, and we're left with just a KB. So what this means is that, well, first of all, PF is neither clear nor strongly clear. Also, it's aliased with another two-way interaction term. Now, this is important because what we saw in the last lecture was that when we look at the ANOVA table with the two-way interactions, some of the two-way interactions only had 2 degrees of freedom instead of 4. This is before we broke them into orthogonal components and broke them up by polynomial contrasts. Right, the general P cross F should have 2 terms. It should have a PF and it should have a PF squared, and each of these is going to have 2 degrees of freedom associated with it. So which sum up to become 4. And similarly with K crossed with B. And in this case, we would have a just KB and a KB squared, each with 2 degrees of freedom. But what happened is that which ones? These ones are aliased with these ones. So whichever term comes first in your ANOVA table is going to get 4 degrees of freedom, and the other one is only going to get 2 degrees of freedom. But if you reversed the order in which you display your factors, then it's going to swap. And this was quite tricky, as we saw in the last lecture, because sometimes you can get significance if you have all 4 degrees of freedom, but if you lose those if you go down to 2 degrees of freedom, then we didn't see the significance, and that can be a really tricky part and something you have to be really careful with when you're analyzing your data, because you may have a significant signal coming from one of your interactions or one of your factors, but you might miss it if you just typed in your factors in a different order, and not the wrong order, I should say. There is no right or wrong order because arithmetic is commutative, right? But the way that R displays it, you might miss some significance. And that's why, just to emphasize what we did last time, we'll say last time we fixed this with stepwise variable selection. which is a really good thing to be aware of, because you think like, oh, variable selection, that's for high dimensional regression where I have lots of predictors and I just want to throw away the redundant ones or the useless ones. But it does apply here, even when we have orthogonal designs. It still can be quite useful in a design of experiment setting, as we saw in the last lecture when we looked at this data in RStudio. All right, so that was the main takeaway that I wanted there. Last time, oh yes, a couple things I wanted to show you in this sort of mini part follow-up lecture. And let's see if we can copy this over without ruining my recording, as I always hope. Come on, Microsoft, don't fail me now. All right, so what I wanted to note was that last time we saw that the PF linear contrast was very significant. Remember what we saw last time? We saw that there is some significant interaction between P and F, the factors P and F. And furthermore, when we used the orthogonal, when we used the polynomial contrasts, what we found was that, remember, we looked at linear, quadratic, linear, and quadratic. But all of the significance was hiding in the linear term, in that 1 degree of freedom corresponding to that term. And what I said is that we can actually see that visually if we plot the means of the factors. So I have a plot of this that I didn't show last time because I didn't have the code ready to plot it, but I had it ready in my lecture notes here, so we can look at it now. So do you recall, I think it was either 2 lectures ago when I was trying to explain polynomial contrast, I drew those box plots and said that, well, if P and F, for example, change linearly, like if there's a strong linear contrast, then that means that the linear contrast should be linearly changing. And that's actually what we see here as displayed. So when F, for example, is set equal to 0, we see a strong increase in the yield for factor P. As we go from none to a small amount to a large amount, the yield, or the output of our sugarcane crop, grows drastically from, I forget what the units are, but under 3.5 to over 4.5. But when we have F set to 1, we're already starting at a higher level, and we still increase, but we increase at, say, a lesser slope. In fact, by the time, I guess 1 and 2 are kind of hard to distinguish here, but roughly you could think that we're linearly increasing, but at a slower rate. By the time we get down to F being set to a high level, well, now it's just sort of flat, which means that in some sense, if F is set to 2, if we're putting a lot of F in, I honestly forget what F is, so I'm just saying F. If we put a lot of that in, then it doesn't really matter how much of P, which I think was phosphorus, if I remember my things correctly, right? The blue line looks really flat. So that's telling us that if F is at a high level, then we don't really need any phosphorus if we've already applied factor F at a high level. And similarly, the converse is true in the other plot. Here, I fix P at level 0, and we see a pretty steep increase in the output as F goes from 0 to 1 to 2. So this means that, yeah, we want to increase F as much as possible, at least to level 2, to get a better output for our sugarcane crop. We see less of an increase when P is set to 1, and we see a pretty flat line here when P is set to 2. So again, if we put a bunch of phosphorus into our soil, then it doesn't matter what we do with factor F. The 3 blue points are all kind of in a straight line. Okay, there's a little bit of noise here. Maybe at 0, it's a little bit lower than it is at 1 or 2, but this is roughly what I mean by a linear linear contrast, the idea that we start with a steep slope, then we move to a less steep slope, then we move to a flat. And we could keep going, right? I think in the the example I gave 2 lectures ago, we started with a line going up, then a line flat, and then a line going down. That would be an extreme case, but as long as the slope is changing linearly, that is, we're having a linear but a linear crossed with linear contrast that is significant here. So this is a really good example, I think, to sort of visualize what's happening when you have 2 polynomial, like a crossed polynomial contrast, like linear crossed with linear. And again, this is probably about as complicated as it's going to get. As I've mentioned more than once, when you have these factors, it's unlikely that you're going to see something at a 3 or higher way interaction, especially with these polynomial contrasts. I mean, at least if you have a linear crossed with linear contrast, you can think of it as in a 2-dimensional plane as like a surface. So if I have one direction for f and one direction for p, and my response is the z-axis, then I would have like a flat plane kind of there. But if you're in higher dimensions, it just gets even harder to sort of visualize what's going on. But it doesn't hurt to check it, but it is one of the reasons why we often strongly prefer to use fractional designs when we have factors that have 3 or more levels in them. All right, so we got that. Oh yeah, I did have one other table that I can show you, just because it's kind of interesting to see that I can also copy over into the notes here. And that was the P and F average yield values. So if we look at the average yield when P and F are set to 0 and 1 and 2 and so on, we get a table that looks like this. So this is the table version of these green and red dots that we're staring at in the plots up above. But we do see that when neither are present, we definitely see a drop in the yield. And when at least both are present, we see an increase of over 5, right? And when only one is present, well, we're somewhere around 4 or 5, like 4.5, maybe 5 if one is set to a high level. But this is just another way that you can visualize or try to look and see what the interaction is between P and F. And when you would have numbers like that, you would see some type of strong interaction. If there was no interaction, it would look kind of random, I guess. Or I guess the rows or the columns would all look about the same as you moved through them, but there wouldn't be any changes from one to the next. Up to noise, of course. Yeah, so the other thing I wanted to mention very quickly was that we discussed in the last lecture that the block is actually partially correlated. It overlaps one of the factors. It's a very strange kind of occurrence because the block factor actually has 8 levels. But it has 9 levels, 8 degrees of freedom. So we have a 9-level block factor, and then we have 3-level experimental factors. And one of those experimental factors, I honestly forget which one off the top of my head, is confounded by the block. But what we can do is we can actually plot the all of the contrasts. We can plot the correlation of the polynomial contrasts, and you get some kind of crazy plot that looks like this. So this is actually an image plot, a matrix plot, and what we have here, it's kind of hard to imagine, but this is all 0 correlation here. This on the main diagonal is 1. A correlation of 1 because every factor is correlated with itself perfectly, and every row and column of this matrix is going to be some polynomial contrast, like A linear, there's going to be, not A, there's no A in this, N linear, maybe NP linear quadratic, etc. And every pixel is going to correspond to a correlation. So most of the things that we have, most of the factors here we have are uncorrelated. until we get to the polynomial contrasts, the two-way polynomial contrasts. And what we saw before, right, is the same when we had P crossed with F, and what was it? The other one that was aliased with it, K crossed with B. Right, we had K crossed with B. Now, since these two are partially aliased with each other, their polynomial contrasts are partially correlated. So these yellow and red dots are, well, I don't want to say partial correlation because that's a separate, partial correlation is a whole separate concept in statistics. It's, we'll just say it's a correlation that is strictly between 0 and 1. So it's kind of a strange thing in design of experiments, because in design of experiments, typically we either have 0 or we have 1. Either two factors or two terms in our model are completely uncorrelated, they're orthogonal to each other, or they coincide and they're perfectly correlated. In this case, some of these polynomial contrasts for the two-way interactions are correlated somewhere between 0 and 1. And this is another reason, I'll say, another reason why variable selection is useful. Because if, for example, you took the course I did in regression back when we were actually teaching in person, one of the things I talk about is the idea of multicollinearity. When you have two predictors in your model that are highly correlated, you typically want to just pick one of them and not include both of them, or else you get big increases in the variance of your estimators and your predictions, which is bad. And we would use stepwise selection to pick which variables we should keep and which we should throw out. And the same thing happens here. You have all these correlations, so that's one of the reasons why using the step function in R, step, is actually a really useful thing to do. In the second correlation plot here, we have this weird little section here, and this is this corresponds to correlations with the block factor. So that's another weird thing that happens. This block factor is partially correlated with a bunch of other factors in the model, which makes it a little bit complicated to analyze compared to if it were just completely, say, orthogonal to everything, or completely confounding certain factors but not confounding others. In this case, it's almost like a partial confounding, I guess, since it's a block, if that's the right terminology. All right, so that's more or less everything I wanted to talk about this data set, so we can wrap up with a quick little 30-minute discussion, slightly under 30-minute discussion on this data set. So I would encourage you to look at this yourself and try it out and just try to explore this and other data sets. And if you have questions, please come and talk to me, because it can be a little confusing to look at first. It was 1953 that this was this data set came from. So yeah, it is quite an old data set. But anyway, yeah, the last thing I had in my notes was just a reminder to reorder. Be careful about reordering your terms and using the step function, and we've covered all of that. So we're going to take a break, and then I'm going to go do some response surface methodology in a separate video. So I will see you in that lecture.